axis. It doesn't have to be a fixed axis. So the outcomes for today's class are ability to analyze general planar motion, okay? Then the difference between static and kinetic friction, and then how to analyze when a wheel rolls or slides. And I'll do a problem on that. I think that's a fairly hard concept, so I'll spend a bit of time on that. So a rigid body, which is essentially two-dimensional, is acted upon by various forces. These are external to the body, F1, F2, F3, and can be external moments too, M1, M2, and so on. And G is the center of mass, and let's say that alpha and omega are the angular acceleration and angular speed of the rigid body. So, equations of motion. By the way, this is a free body diagram because I've shown the influence of all forces on the body. There are three equations of motion for planar motion of rigid bodies. The first one is the net force in the x direction is mass times acceleration in the x direction. Specifically, this is acceleration of the center of mass. Fy is mass times acceleration of the center of mass in the y direction. And the third equation comes if you take the moment about any point. So a special case is when you want to take the moments about the center of mass, in which case this would be Ig, which is the inertia about G, and the axis of is along the axis of rotation. So in this case, the axis of rotation go through the plane of the paper. They come outwards, right? Because the body spins in the plane. So the axis would be given by your thumb if you curl your fingers along alpha or omega. So as I said earlier in the previous class, sometimes you are better off not writing the equations of motion, well, not writing the moment equation about point G, because what happens is you might want to eliminate certain forces, and so you're better off taking moments about a different point. Let's say that you want to take moments about point P. Okay, so sometimes you might want to write equations of motion as Fx equals magx. So this is the first two equations remain the same. However, what I'm interested now is taking moments about a point P, okay? And point P is chosen by you. It doesn't have to be a specific point. It can be, for example, it can be this point. If you take the moments about this point, about the point where F3 acts, then clearly the effect of that force on that moment is going to be zero. So that's a way in which you can eliminate certain forces. So you want to find the point at which maximum forces pass through and take the moment about that point, and that will make your life easier when you do the problem. Now, both these equations will give the same answer, okay? Answer will not change, but it's judicious to use a moment about a different point, MP. So what happens is if you take moment about P, the equations become slightly more complex. It's Ig times alpha plus, you'll have to basically do a cross product of the vector from P to G. So R G to P to G crossed with mass times acceleration of G. Okay, now there is slight abuse of notation here. This looks like a scalar, this looks like a scalar, and this looks like a vector. But really what happens is this will be in the k direction. k is a vector which points out of the plane of the paper. So let me rewrite that. And when you take the cross product of two vectors which are in the plane, so the vector r, p to g is some vector in this plane of the paper, and acceleration g is another vector in the plane of the paper. When you take the cross product of two vectors in the plane of the paper, the net product is given by the cross product is given by curling your fingers from the vector r to a, and that vector always points in the k direction or out of the plane. So this thing, whatever you get here, will be either in the k or minus k direction. So it could be pointing inside or outside, but it will never be along the I and j direction. Okay, that's a check. So this whole equation is a single equation because all the moments are either in the k or the negative k direction, so it's clockwise or anti-clockwise moments, and everything here is a scalar. So this is another way of writing the equations of motion. And as I said, they are the same equations. If you write, for example, if you start solving this problem and you write fx, fy, and you write mg and mp, don't think that mp will give you a different equation. It's going to give you the same equation. There are only 3 equations for Newton's laws for a planar body, not 4 equations. So you might think this, and this one is the unique equation. That's not the case. Okay. The reason why this is slightly different from the previous class. I told you that you can write mp equals I about p times alpha. Remember? So last class we wrote mp is ip times alpha, right? You cannot do something like this for general planar motion, and the reason is because when the body is accelerating, the point P is accelerating. When point P accelerates, you cannot use this equation. So cannot use when P is accelerating. In this case, you need to use this equation. Use 1. Okay. Only when P is stationary or when P is moving with uniform velocity, that's when you can use this equation. Okay. So for example, for a pendulum, right, you could use that equation because the axes were fixed, not moving. If the pendulum was moving with uniform speed, you could still use this formula, the second one. However, if the support of the pendulum was accelerating, you cannot use this formula. You have to use this one. That's the difference. I don't know if the book mentions that, but you cannot use. That's why we first learned about fixed axis, and then we are doing general planar motion. Okay, so again, we are doing this the same thing which we did in chapter 13 in other parts of chapter 17. We always draw a free body diagram, write the equations of motion, and then solve for kinematics. Okay, so here is a problem I just made up to illustrate what I just talked about, rolling and sliding. Okay, so a 20 kilogram wheel has a radius of 0.1 meters. The coefficient of static and kinetic friction is 0.3 and 0.2. As you notice, mu s is greater than mu k. If a force of 300 Newton is applied, find the acceleration of center of mass g, assuming g is 10 meters per second squared. Now, what you're not being told in this question is if the wheel is rolling or it's sliding, and you cannot assume it's rolling or sliding unless you do the calculation. So what I'm going to do is I'm going to assume that it rolls. It's always good to start with that assumption as opposed to the other one. Find if the condition for slipping is true. The condition for slip is friction force is mu times n, mu times mg. And if I get a contradiction, then my assumption of rolling of the wheel is not true, and then I'll reverse the assumption and resolve the problem assuming it's sliding. So you solve, assume rolling, you check the conditions. If that doesn't come out to be true, then you change your condition to sliding and solve the problem. So let's solve this and just pay attention to how this proceeds. So first is draw a free body diagram of the wheel. So this is a free body diagram. It will have all the external forces, mg, the normal force, the force F, and then as I told you earlier, the friction force will always oppose the motion, so it's going to be this direction. Let's call it FF. Okay, those are the only forces acting on the wheel. Okay, so let's call this G. Next, equations of motion. Okay, so this is an example of general planar motion, right? Because, well, you could say that, well, it could be motion about fixed axis, like it could be motion about point A, but you don't know if A is slipping or not. If it's not slipping, then yes, it is motion about, it's almost, you can use what you learned in the earlier part to solve this. That is, you can take inertia about this point and solve it. But if it is slipping, the acceleration is not equal to 0, then you cannot do that. So it's safer to assume it is general planar motion and solve it, rather than make an assumption that it's that point A is fixed. So I'm going to use the second set of equations. So I'm going to use basically, I can use these equations or these equations. It's up to me. Okay, so Fx equals mass times acceleration of g in the x direction. So that gives me the net force F minus Ff, which is acting in the negative y. So if you like, this is I or x, and this is y, equals mass times ag. So this is, mass is 20, so 20 times ag, and I'm going to drop the suffix x because I know that this wheel cannot accelerate in the y direction. If it did, then it wouldn't be on the ground, it will fly in there, so it's not true. So then Fy equals mass times ag y. So the net force in the y direction is the normal force, and then there is mg acting downwards. The net acceleration in the y direction, as I said, is 0. So n equals mass times gravity. So that's, so I said g is 10, so mass is 20, so 20 times 10 is 200. Okay, now a choice of writing the moment. I can put moments about any point. I can write moments about this point A. I can write it about G. The reason I would write it about A is then the friction force would just disappear from my equations. I will leave it. But let's, for this problem, let's just use the first one, and then the next problems I'll try to do it about a different point. Let's do mg is ig alpha. So this is all the external moments about g due to external forces. Okay. So the external forces on the body are mg, there's n, and f and ff. Now n, f, and mg all pass through g, which means that the net moment at g due to those forces is 0. The only force which contributes towards mg is the friction force because it acts at a distance from g. So the friction force times the moment arm. The moment arm is basically the radius of the wheel. So let's say this is r. So what's the sign on the moment? It's negative, because if you now hold the wheel at its center point, then this force is going to turn the wheel in the clockwise direction, as you see, right? So it's going to be negative. Equals Ig times alpha. Okay, and R is 0.1. Ig for a disk is mr squared divided by 2. I'll write it down here, half mr squared divided by 2 times alpha, so it's going to be half times 20 times 0.1 square alpha. And once you do the simplification, what you get is ff equals alpha. Okay, let me write this down, this equation down again. This basically gives me f minus f. What's that? Oh, minus sign. Yeah. Well, let me just assume that alpha is clockwise. So if I assume alpha is clockwise, then this is going to be minus alpha. Minus alpha. Just to make my life easy. This is okay, because this is CCW. Alpha is clockwise. It's going to turn the clockwise direction. So I'm going to start with the assumption that alpha is clockwise. It's perfectly fine to do that. So FF is minus FF is 20 AG. Okay, so that's one equation. This is the second equation. This is the third equation. Okay. So I have three equations. Okay, now I'm trying to solve for acceleration g, because what's asked is find the acceleration of center of mass g. So I have three equations. And how many unknowns? F is known. F is, I think F is 300. Two unknowns? Equation 1, 2, and 3. How many unknowns? There are three unknowns. I think there are four. F is unknown. Alpha is unknown. Well,
you said F was known.
Alpha is not known.
You said F was known.
F was known. So AG 1, FF is 2, N is 3, and alpha is 4.
It's just 200.
But if you count it as an equation, then you have to consider it as an unknown. Okay, so you could think of it this way. What you're trying to think of is, let me not think of equation 2. I know n, so I'm going to think of equation 2. In that case, you have two equations and three unknowns. So you're saying equation 1 and 3 are your two equations, and your three unknowns are F, F, alpha, and AG.
But we can't calculate for FF because you already know what is next.
You don't know what the friction force is. As I said, the friction force depends on the condition.
So we have no AG is. NG is equal to N, so we know what is.
So that. I'm going to get to that. So that part is part of where we consider slipping or no slipping. So that's the next part. I'm going to do that. But right now, as it is, depending on how you think, if you like to think three equations, then there are four unknowns. If you like to eliminate equation 2, then there are two equations, 1 and 3, and still three unknowns. Which means that you have more number of unknowns than equations, no matter how you do the counting. Okay, so we need another equation. So that equation, the fourth equation, comes from the no slip condition. Okay, so let's do the last part, which is kinematics. So right now, the way I've set the equation up is I have not assumed the wheel is slipping or not slipping. That condition is not there in the equation. And the reason I've done it that way is because then I can, once I have the equations for the generic condition where it's not slipping or slipping, then I can analyze two special cases. It's slipping or it's not slipping. Okay, so that slipping, not slipping gives me the fourth condition, and we'll see how to do it from there. So kinematics. So assume no slip. Okay, if you assume no slip, then what you're trying to say is that this point A is not moving, it's at rest. When the point A is at rest, the acceleration of g is r times alpha, right? Acceleration of g is going to be r times alpha. Okay, so this is our fourth equation. Okay, now we have four equations and four unknowns. Ff, alpha, ag, and n. So four equations, four unknowns. So you can solve for all the four unknowns because you have four equations. Okay, so I'm just going to write down the answer just because in the interest of time. So if you basically do the math, then what you need to do is, in this case, is to check if your condition that no slip is true or not, right? You are not told that it is rolling or that it is not slipping. So you got to check that. So what you do is you find f. What I get for f is that it is comes out to be f divided by 3, or 100 newtons. Okay. How do I get this? Well, I can solve from four equations, four unknowns. I get that. Okay. So that's 100 newtons. The condition for no slipping is that f should be less than mu s times n. Right? What's mu s? Mu s is 0.3. So 0.3 times n is 200. So that comes out to be what, 60? So is 100 less than 60? So 60. So it's not true, right? So if the friction force is coming out to be less than mu times s, then it's true that it is rolling. Otherwise, it's not true. Which means that our assumption was wrong. Okay, it's wrong, which means that it's actually slipping. So what we have to do now is resolve the problem assuming it's slipping. So what I have to do is, what I'm going to do is do the kinematics all over again. Assume slipping. Okay, so when the wheel is slipping, right, then just like my example of the sliding block, the friction force caps at mu times n. So in this case, I know that the friction force is mu k or s, mu k or mu s. When it's slipping, what's mu? When it's moving, what's mu? Mu k. Mu k is the kinetic friction when something is moving. Mu k times n. Okay. So what happens is this thing now is my fourth equation. So what I would do is now is use 1, 2, and 3 Okay, 1, 2, and 3 are still valid. They are for a generic case when it could be slipping or rolling. So 1, 2, and 3 are still valid. And the fourth equation, let me call it 4b. So that's not confused with the other one. So this is 4b. Okay, now 1, 2, 3, and 4b are my equations. And FFN AG alpha are my unknowns. So I again have 4 equations, 4 unknowns, and I can totally solve for those 4 unknowns. So it's just a matter of doing the algebra now to find AG. Turns out that AG is 13 meters per second square, and alpha is FF equals 40 newtons. Okay, so this is the thing which we were interested in, AG. Okay, and you'll see that actually AG is not equal to R alpha. This is the rolling condition. Sorry, AG equals R alpha is a rolling condition. AG is not equal to, AG is 13, and R is 0.1 times 40, so that comes out to be 4. So 13 is not equal to 4. So that will not be true. This is not true. This is the condition which you use for rolling. So that's how you solve it. If you're given that a wheel is moving, you cannot assume it's rolling or sliding. You have to do the math to figure it out. That's why this problem says